Hello, my name is Einar Sveinbjörnsson. I'm head of the Faculty of Physical Sciences. Physical Sciences is chemistry, math and physics. And in this small video, you're going to get a glimpse of the activities that we have within our faculty. We basically are located in 4 buildings. We will walk you through these buildings and discuss with actually only a few of the people around. We have the coronavirus outbreak now, so as you might notice that people are wearing masks and we don't have the same populations in our buildings as we used to. But I think we have we're going to give you a cross-section of the activities in physics, math and chemistry.
Hi, hello, my name is Kasper. I'm a postdoctoral researcher here at the University of Iceland, and in the astrophysics department we study a lot of different topics ranging from dark matter to the exploding death of massive stars. But what I've been currently working on is a fairly new phenomenon called fast radio bursts, who was first detected roughly a decade ago. And it's still a puzzle what causes these fast radio bursts. The only thing we know is that it's a burst of radio emission that happens at the radio frequencies, but only for 1/1000th of a second. And we still don't know what causes these fast radio bursts. But theories, they range from something related to black holes or perhaps neutron stars left after the exploding supernova. So even though we don't know what they are, they're still extremely useful as a probe of studying whatever is in the vast universe around us. So basically a fast radio burst, they can explode several billion light years away and then travel through the universe. And similar to how if you have a white light which gets dispersed into all its different colors when you put it through a prism, then the similar thing will happen to fast radio bursts, where all the different matter between us and the fast radio burst, several billion light years away, will get dispersed in the same way. And when we measure this dispersion, we can get a sense of how much matter is actually distributed between us and the fast radio burst. And this tells us something about what the amount of matter that fills the universe, which until recently we couldn't detect. So we knew that it had to be there, but we couldn't detect or see roughly half of it. But with these new fast radio bursts, we actually managed to crack the code and then find this so-called missing matter. And to do this, we partner, especially here at the University of Iceland, we partner with several telescopes worldwide, so around the globe. Most notably, we have a partnership with the Nordic Optical Telescope in La Palma, but we also get extensive data from the Very Large Telescope in Chile and also the Keck telescopes in Hawaii. And we mainly use this data or we get sent this data from the telescope and from the observatories directly up to us for us to analyze. And this is much of this same data. That's also what we use when we teach, especially master students, where we allow them to analyze the same state-of-the-art data that has been obtained from some of these, or from some of the largest telescopes in the world, basically. So we give the students a chance to work on some state-of-the-art projects and state-of-the-art data related to astronomy.
So hello everyone, my name is Gunnar Arnalds and I'm a professor here in physics at the University of Iceland. My specialities are mostly in experimental solid-state physics, thin film physics and material science. So I'm mostly working on research within magnetism, magnetic thin films, magnetic nanostructures and microstructures, specifically there in artificial spin ice systems. Thin film-wise, I'm also working on research on phase change materials, mostly on transition metal oxides, which undergo transitions between metallic or insulating states, and various other topics within solid-state physics. My role here at the university is also as the manager of the University of Iceland Nanotechnology and Material Science Center, which is a collaboration of research groups here at the university which work within experimental physics and material science. This collaboration is basically built around all the infrastructure needed for performing advanced research within these fields. And this laboratory that we have includes a clean room which is here behind me, which was founded in 2006, and since then has been a kind of a pillar of being able to do high-tech and advanced research on material science, nanotechnology, solid-state physics, and it's used in various projects. So the capabilities we have here mostly are obviously focused on microstructuring, so we have facilities there for optical lithography. We have also access to electron beam lithography using a modified SEM system. We have then all the necessary equipment for finalizing products out of this, coating systems, analysis systems, etc. In addition, obviously, to the clean room facilities, we have an extensive and strong laboratory on thin films, mostly on coating systems. The knowledge at the University of Iceland on magnetron sputtering is quite advanced and has laid a very good foundation for research into material science. So in that laboratory we have 2 highly advanced sputtering systems and then a third advanced sputtering system here in the clean room. In addition to this, this laboratory and the University of Iceland Nanotechnology and Material Science Center houses 2 research companies which rely on magnetron sputtering. One of these companies, Grain Research, has its own privately owned 2 magnetron sputtering system, which it uses for technological development and research projects it's working on for international companies. Of course, the facilities we have are used extensively by students. There are numerous PhD students here working on different projects, master students as well. We have a lot of summer project students, even undergraduate students, which work here during the summer on projects involving the instrumentation and the technologies we have here. The projects these PhD students we have working on range from anything from thin film physics, magnetism, electronics, semiconductors. We have students here working on plasma physics. We have students working here on optical properties. We have one PhD student working on combining cellular biology and nanotechnology. So it's a project which mixes together work with live cells and nanotechnology kind of platforms created here in the clean room. Then we have, beyond these coating and sputtering facilities, a few other different labs, including optical labs, electronic labs. We have extensive instrumentation for research on magnetism, for characterizing magnetism, both using vibrating sample magnetometry and optical techniques. So there's quite a lot of instrumentation which we've combined into our lab, which we call then the University of Iceland Nanotechnology and Materials Science Center. A large part of the research we do here relies on a fundamental understanding of the structure of the crystals or materials we're working on. So this here lab is a newly built lab, which we call the Analysis Laboratory, where we have instrumentation for detailed analysis of the structure. This machine here is an XRD machine, an X-ray diffraction machine, which was recently funded by the Icelandic Infrastructure Fund. This is a 300,000 euro instrument, which, at least for a few more months, we can say is the most advanced XRD system in at least Northern Europe, hopefully for longer. It's based on new technologies, which Malvern Panalytical is providing, and we're putting these new technologies already into effect and creating new results on our samples. And we already have publishable results, even though this system has only been operating for less than 2 weeks now. Also in this laboratory we have our atomic force microscope, so we can combine the surface morphology one gets using atomic force microscopy with the kind of inner information on the crystal structure that we gain from XRD measurements, and thereby get a full picture of how the structure of all our material is. And then you can take that further, analyzing the kind of electronic and solid state properties, the electronic, the magnetic, the optical properties, and then one can correlate that to the structure and see if you can play with the structure a little bit better to modify the properties, or if it has some impact on the physics involved in in the kind of electronic structure and the behavior of the material. Structural analysis has always been a part of the undergraduate education here at the university, focusing mostly on the physics student and engineering physics student, but engineering students have also been able to partake in education on how to understand the inner structure of materials. So undergraduate students, mostly in their third year, perform experiments in laboratories on X-ray diffraction. They do laboratories on atomic force microscopy for investigating the surface morphology of different materials. They also look into magnetic analysis, analysis of semiconductors, optical properties, and so forth. So these laboratories which we've set up and tried to have as kind of accessible as possible have always been used and will be in the future for teaching at the undergraduate level. That couples then strongly into master studies, where students can then continue to use the instruments that they learned on, or the instrumentation and techniques they learned during their undergraduate studies, to build on that and make some good master's projects.
So, hello, I am Sigurður Hafstein. I'm professor for mathematics and applied mathematics when I prefer. And I'm also head of the math department. Well, the math department is responsible for a lot of the teaching, also for the engineering students and students of computer science and other faculties, apart from the Department of Physical Sciences like chemistry and physics. My research is mainly concerned with dynamical systems and numerical methods for dynamical systems. In my group now we have 2 postdocs and 1 PhD student and 1 master student, which is kind of typical for that we don't have too many master students in mathematics. Typically for mathematics we don't need too much for our research. We need money to pay people and we need some offices to sit in and think and program. We don't need labs, and actually we do have some supercomputers here that are available to us when we are doing the heavy computations. If I go back to teaching, that we are teaching analysis for the engineering students and the computer science students. So for analysis 1, we offer it in like 3, let's say, difficulties, or applied 1 or practical 1, analysis 1, and then analysis 1 for engineers and physics students. And then it's called analysis 1A, which is then mandatory for math students. And well, some students of applied mathematics and physics also take that one. There we prove all or most of the results. Then for analysis 2, it's similar, but the applied course is then not offered. They only take analysis 1. But we then have 2 and 2A, and then 3 and 4. What is unusual for the math department is probably that we also have a lot of people doing statistics and a lot of research in statistics. But apart from that, our research is, well, it's a lot in complex analysis, where we also have 2 PhD students, and 3 professors are specializing in complex analysis. Then we have algebra, 2 people doing algebra, and combinatorics. And, well, then the mathematical physics, which you will hear about from them directly, so I don't have to talk much about that. And, well, then I'm doing numerical analysis, or dynamical systems and numerical analysis, which comes to differential equations and more general systems. Also, we have pure math, and we also have applied mathematics, which is quite new. It's only a few years old, but it's become larger than pure math already. Most of the students in applied mathematics, they are specializing in statistical methods. And we have 3 people doing that. and they also have a lot of projects and PhD students, and they are also offering a Master of Applied Statistics, which is kind of very important for Iceland or for high-tech society. Scientists and well, people working in industry in all areas, they have a lot of data and they have to evaluate the data. And to do that, you use statistics. And these people not necessarily have a hardcore math background. They have some mathematical background, but not hardcore. So it's very nice that we offer this program for them to get a Master of Applied Statistics, where they really study how to analyze data.
Hello, my name is Iman Mehrabinejad and I am a research specialist here in University of Iceland. As a part of the dynamical system team, we are working on developing some methods to find search the stability of dynamical systems. We are focusing on contraction metrics, and we try to calculate and approximate contraction metrics for these systems and compute the Bayesian of attraction for the system. For a dynamical system and its stability study, it's important to find the equilibrium point or the periodic orbit and their Bayesian of attraction. And this is what we have done here as a part of simulations we did. We both developed a method, we proved it, and now we are doing the approximations and simulations.
My name is Carlos Argaez, and I'm currently postdoc in the Dynamical Systems group under Professor Sigurður Freyr Hafstein guidance, and we are working in dynamical systems trying to develop different algorithms to find solutions to approximations to complete Lyapunov functions to systems described as differential equations. So my work here consists on finding better algorithms to propose complete Lyapunov functions to given autonomous systems and to describe the complete behavior in the complete phase space of the dynamical system. So recently we have released 2 packages to compute complete Lyapunov functions for dynamical systems in any degree in a simple, easy, user-friendly environment. And currently we are working on trying to find better methodology. Actually, behind the screen, there are some small examples of how we have managed to optimize our algorithms and enhance the results. We have managed that iterative procedures usually give better results on describing the behavior of dynamical systems, and especially in the orbits where the systems have periodic solutions, as well as the regions where the systems behave dynamically. At the university, I have also been given the opportunity to teach at a bachelor's level, and I managed to teach different courses between Fourier analysis and numerical linear algebra. And well, currently I will continue working on this, and we hope that our softwares and methods can find application in applied science, for example, to areas in which one needs to dominate a system, for example, be able to describe how it behaves, and that's one of the possibilities of our research.
Hi everybody, so my name is Valentina Giangreco Puletti. I'm professor here in the Department of Mathematics within the Faculty of Physical Sciences. My research area is high energy theory. We are, it's a group, let's say, the mathematical physics group is made more or less by 4 senior permanent people, so 2 within in the physics department and 2 within in the mathematics department. The group has 4 postdocs currently, so these are specialists and postdoctoral fellows. We have a total of 4 PhD students and 1 master student. As I say, it's a kind of interdisciplinary area in the sense that some of them have more a background on theoretical physics, some of us are more mathematical background, and we are working mostly on 2 main lines, let's say. One is more in the direction of statistical physics, random geometry, and so this means from a mathematical point of view, it's I would say probability, combinatorics. The other, random geometry, the other side is more on the high theoretical physics, so high energy physics, in a broad sense string theory, and we have people working on quantum field theory, conformal field theory, and string theory, of course, black hole information paradox, and also so-called gauge gravity duality. So it takes quite a lot of that. So the group is so the non-permanent positions are mostly funded by personal grants. So these are grants obtained with the mostly money are coming from the Icelandic Research Fund. There are also a bit of local funds that support some of the postdoc, typically 1 out of 3. PhD students are all funded through the Iceland Research Fund. Usually this fund is for 3 years, so the PhD might finish the 4th. If they need a bit more, we usually use also local funds like the teaching assistant grants. So it's funded by the university to finish maybe to have an extra year, 4th year. I'm teaching mathematics since, as I say, I'm in the mathematics department, so I teach mostly analysis, all different kind of real analysis and differential geometry right now. And so my other colleague is in the same department, Sigurd Orn Stefansson, is also teaching analysis and graph theory, usually. And then there is Thordur Jonsson and Lars Torlacius. They are in the physics department, and they are teaching courses from quantum mechanics to general relativity, and of course other physics.
Welcome to the Science Institute. My name is Sigríður Jónsdóttir. I'm a head of the chemistry department, and my education is I did chemistry in Iceland, and then my education is in Germany, diploma chemistry, and then PhD in Germany. In this building you will find the research facilities of the professors in the Department of Chemistry. On the top floor, where I'm located at the moment, we have the offices, but downstairs in the first floor and in the basement, in the first floor we have the laboratories, and in the basement there are mainly equipment, research equipment for chemical analysis, where all our students and our professors, they have access to these instruments and are using them for identification of their compounds. In this building, we have research facilities for organic chemistry, inorganic chemistry, and physical chemistry. We have at the chemistry departments, we have 3 persons in organic chemistry, professors or teachers. 2 of them are professors and 1 assistant professor. And they have laboratories downstairs. One of them has been renovated, and one of them is waiting for his new lab to be finished, and you may be able to see that in the video later on. and they all have access to all our instruments. In the inorganic chemistry, we have two professors, and then in the physical chemistry, we have 3 people, or 3 or 4 people. Only 2 of them have their research facilities in this building, but other Professor Hannes Jonsson, his facilities, what he is using is in a different building. We have a 400 megahertz Bruker NMR. We have an ESE Bruker mass spectrometer downstairs. We have fluorescence spectrometer. We have access to infrared in the teaching building. And then, of course, in the labs, each professor has equipment really he needs to use. And, of course, I should have mentioned that in the basement, we have also an X-ray instrument for X-ray analysis of single crystals. That instrument is the newest one in the building, and the NMR will be renewed now in the coming months when we are going to exchange the console for the NMR. We have the need to have a bigger NMR in the future, but that is another story. And also down in the basement, in the first floor, we have labs for the biochemistry teaching staff, but they will be moving out from this building into Askja in the coming months, but that is another story.
My name is Snorri Sigurðsson. I'm a professor of organic chemistry, and I arrived from the University of Washington, where I was on the research faculty in 2002. My area of specialty is nucleic acid chemistry. I incorporate the spectroscopic probes into nucleic acids to study their structure and dynamics. I've mostly been working with persistent organic radicals like nitroxides for use with electron paramagnetic resonance or EPR spectroscopy. In recent years, I have been designing and making biradicals for dynamic nucleopolarization, which is a technique that is used to increase the sensitivity of NMR spectroscopy. When I arrived here, I moved into a newly renovated laboratory for 4 people. And a few years later, I received a grant of excellence, and then I got access to another laboratory for 2 people. And in the last years, there have been anywhere from 5 to 9 people in my laboratory working, but most of the time we're anywhere between 5 and 7. The people in my laboratory are mostly graduate students, PhD students. Once in a while there's a master student. Right now there's one master student working on a 90-credit research project. There are 2 concerns that I have and have had for some time, and those are both related. Firstly, it has to do with the facilities. We are here at the Science Institute, and this building is in severe need of renovation, and space is also very limited. And this is in particular for the experimental chemistry. So maybe I should add that for the facilities, space has also been a big issue, although that will not be an issue moving forward because biochemistry is moving to a different location. So I'm actually not certain if renovation would be advisable in this building, because this building was never designed for this for chemistry. The second has to do with the young faculty, the new beginning faculty members, and that is also related to the facilities. There is the limited space and lack of space. And I think the example, for example, for our most recent faculty member, Benjamin, who was hired there in 2017, he has yet to move into his laboratory. I think that is serious for someone where the tenure clock is ticking. The other part has to do with startup funds, and it's really expensive to do experimental chemistry, and there is hardly any startup funds here. And I would just like to use myself as an example of someone that got all the support that I needed. When I arrived here, the university had not been split up to 5 schools, and the president of the university had a small fund for special projects. And I was able to get the 10 million Icelandic kroners there to buy instruments. And I'm sitting here, for example, by a nucleic acid synthesizer, and this was really a key thing for me to be able to carry out my research. Over there is an EPS spectrometer, only one of a kind here, which I use routinely. And then there are, of course, HPLC instruments, centrifuges, rotary evaporator, all of that. And so I was very fortunate. I think this is something where we could really improve, is to support the young people better. Thank you.
My name is Hannes Jónsson, and I'm a professor of theoretical chemistry here at the University of Iceland with research facilities in the Science Institute. I'm an adjunct professor at the Brown University and adjunct professor of applied physics in Aalto University in Finland as well. I was at the University of Washington professor for 15 years in Seattle before moving back to Iceland. My research group is fairly large. I have 10 PhD students and 5 postdocs, and we're all working on computational methods, computational chemistry and condensed matter physics. And a large part of the work involves development of algorithms, software, and this involves approximations to basic equations of physics as well as numerical mathematics. And the goal is to find, for instance, the mechanism of chemical reactions, how these events occur, and both to interpret experimental measurements and to be able to predict possibly some things that have never been measured before, so as to guide experimental efforts. The methods that we develop are applicable in many different circumstances. For instance, methods we have developed to find the optimal path of chemical reactions is now being used to trace radioactive waves in the ionosphere, and we're applying them now to propagation of seismic waves in the Earth's crust. So these methodologies are very interdisciplinary, and we work on various aspects of these things. Some of the applications are, for instance, the reduction of CO2 to form fuel or chemicals for chemical industry, magnetic skyrmions, so-called, for possibly higher density data storage and manipulation in future technologies. So it spans a wide range of applications. The equipment we use is high-performance computing clusters, and I have been involved in the setting up and development of facilities of high-performance computing here in Iceland, and now serve as head of the steering committee for the Icelandic Research High-Performance Computing Facility. So some application projects that we are involved in are, for instance, the reduction of carbon dioxide to form fuel and other and chemicals that could be used in the chemical industry. So the idea here is to use electrochemistry for doing this. So one could sort of plug in and use electrical current to reduce the CO2 and form, for instance, methanol or even ethanol, and this can then help reduce the global warming and so forth. In order to do that, we need to figure out better catalysts for doing this, and this involves searching for materials, for instance, nano clusters and different compositions that can make this viable. It is proven that one can do this in principle, but the problem is that it's not commercially viable at the moment. So this is an example of ways that we can help search for better materials more efficiently by computer simulations, and then point to certain candidates that are most likely to work for in experimental studies. Another application would be the development of magnetic materials that are hosting so-called magnetic skyrmions, highly localized non-collinear states that can be used for higher density storage of data and possibly manipulation of data in future devices. And the idea there again is to figure out what materials have skyrmions that are long-lived enough and can be manipulated easily enough. So again, it's a matter of searching for the right materials for this future technology. Again, something that is faster and easier done by computer simulations that then can be verified and checked by laboratory experiments. The methodologies we have developed for these kinds of things are then used in all kinds of other disciplines, and we are also working on geochemistry and the reaction of CO2 with minerals such as olivine, and this relates to the Carbfix project, for instance, where CO2 is mineralized in the ground. And we are also using similar kinds of methods for chemical reaction studies to study, for instance, seismic wave propagation, electromagnetic wave propagation in the ionosphere, and several other things. The interesting thing about numerical calculations that the same algorithms can be used in many different contexts. In fact, the algorithms used by some people to simulate collisions of galaxies are very similar to the algorithms we use to simulate liquid water. So that's the interesting thing about these computational science studies.
Hi, I'm Krishna Kumar Damodaran. I'm the head of chemistry teaching. So I'm an inorganic chemist. My research orients around X-ray crystallography, inorganic chemistry, supramolecular gels. And here you see this is a machine we have. This is a rheometer. This is used to determine the strength of supramolecular gels, thin films, and other materials as well. Basically, we just do this mechanical strength for the supramolecular gels and some inorganic gels as well, metallogels. We also use single crystal X-ray diffractometer to get the solid state structure information. And there have been a lot of students using these facilities, to learn. And this is a part of our curriculum, which is taught in Inorganic 4.
So now you have seen the video that is giving an example of the activities that we have within our faculty. Normally, you would have come here and spent maybe 1 or 2 days walking through the buildings, but this time you will see basically a concentrated view of our activities. But I hope it's been helpful, and I hope it will also be helpful when you're evaluating the self-review report that we have submitted to you. And I thank you very much for your attention.